Zoom tomorrow, I can give part of my talk. Has anyone used MongoDB? So, have a few people. Okay, so what I think I'll do is I'll just give an introduction and we'll go through just how you can use it, what it's all about, and then I can just talk about how some of the scaling features that may be useful for you, depending on how you deploy it and what your needs are. And then we'll just do general questions, and maybe we can do some stuff on the console if you want, or we can talk about some new features coming up. It's kind of up to you guys, really.
Maybe just before you start, so Ross was so kind to bring a couple of booklets, I think.
Yeah.
So the persons who ask the most intelligent questions get them first.
Yeah. Cool. So this is my talk from tomorrow. It's quite a long talk, so I'm not going to go through it. I'm going to go through some things quite quickly because some of you guys already know about MongoDB. But basically, I'm going to talk about who 10gen is. And why MongoDB was created in the first place, and then we'll talk about how you can use it, and then we can talk about how it scales and some of those aspects. So, the initial origins of MongoDB. It was founded in 2007 by Dwight and Elliot. Basically, Dwight and Elliot both worked at DoubleClick. In fact, Dwight created DoubleClick, or was one of the original founders, and DoubleClick sold to Google in the, I don't know, early 2000s, late 1990s. DoubleClick, they had a huge problem was about scaling out their data. They had to keep creating custom sort of databases, custom sharding, custom caching layers, all these kind of things. Because after a while, you can go to a bigger and bigger box, but when you're serving 20 billion ads a day, there aren't big enough boxes to scale up to. So then you have to start spreading out the load across multiple machines. And so that's kind of where they'd come from. Both of them worked at ShopWiki afterwards and did exactly the same thing. They built out lots and lots of their own custom sort of database layers to kind of scale up. So in 2007, they started another company, 10gen, and wanted to create a platform as a service. And they saw it as a gap in the market and started working on that. And one of the first things they worked on was the database aspect side. They wanted a sort of a rich database to use. And as it turned out, they scrapped out the rest of the sort of database, they scrapped out the rest of the platform as service stuff and just focused on the database because that had people excited and they knew that's where they could go. In terms of the company, we have had a bundle of funding. We've just got a load through as well. Recently, we're growing massively. The adoption is going through the roof on all sorts of projects, and we can give some examples later. And now our team has gone truly global. We have support people around the clock. So based in New York is the headquarters, California, and then we have Ireland and UK and Europe, and now Australia. So I very quickly mentioned about scaling up databases and illustrating this is, and this gives like a basic example of like you launch and then you get more and more people and how you have to scale up and you have to buy bigger boxes and how that costs a lot of money. And the other side of it is you actually, to be able to cope with massive amounts of load, you spread out your data, you do custom layers, and all these kind of things to denormalize your data and handle the load means productivity, again and again in their examples, went down and down as you try and just be able to deal with load. And this is sort of the general evolution in computing, full stop. People have changed the way they develop. We do more stuff lots more agile. People do continuous deployment all the time. We have new sort of hardware, and people deal with lots and lots more data. So I think an example, in 2000, Google had 1 billion URLs in their index. 2008, they have, 1 trillion. And now, so there's volumes of data is going up exponentially almost. And now even Twitter in 2012 produces 243 million tweets a day. So people are dealing with massive amounts of data, we're exploding it out, and the database technology needs to be able to deal with that. So MongoDB goals are to be able to scale. We can't have joins because they don't scale across massive shards. So to get around that, they needed a fully formed database. They use JSON style documents. And this allows you to sort of embed or have rich data models with just a single place of location and locality to be able to go out and do your queries, grab that from disk and use it. The other requirements are it had to be a proper database. They didn't want just a memory layer for their caching. They wanted to be able to query it like ad hoc, like we do an ordinary SQL database, which meant they had to have secondary indexes, like a SQL database, sorting, easy updates, and you had to have special updates for dealing with complex documents as well. Some levels of aggregation, sort of basic aggregation, counts and grouping. And finally, the main part is the way they deal with scaling. So you have to be able to scale your application with no downtime. That's one of their main goals. They couldn't have downtime when they're doing ads back at the DoubleClick days and ShopWiki. Downtime was costing them money, so they wanted to increase capacity with little or no downtime. And then the other thing is they didn't want to redeploy your code every time you added a new node in to your set. And the other things they like, Dwight's a massive fan of simplicity, so no configs, should work, do the right thing out of the box, and 99% of the time it does. There's one area where arguably it doesn't, and the other side, it has to be easy to deploy and manage. So, just go through some examples in a moment, but our terminology, we don't have tables, we have collections of documents. We don't have rows, we just have JSON-style documents. And every document in a collection can look totally different. So there's no enforcing of a schema, it's how you need to use that data. Generally though, they all look very similar because people don't have chaotic collections, they order and keep things together normally, but basically you have a complex document. Indexes are the same, you don't have any joins or so to be able to scale you either have complex documents which have like subarrays in or sub-documents in there, or you can link off, which is 2 round trips. You'll go and have an ID, and then you'll have to get your application code to go and call and do another query to fetch back the documents that match. Partitions, partition keys, and sharding shard keys are the same thing. So if we have a look at a document and what kind of we mean by flexible schemas, here this is just using the JavaScript shell. But this is just creating a document. This is a JSON object. It's about a blog post because all our examples seem to be blog posts. But they give a good example of what you can do. So we have like tags as an array. So we have that embedded in there, and then we have a date, which is a date object. And when you want to use it, you can just call the command line and use the save command, and that'll put that into the database for you. Then when you do a find, you'll get your document back. And the differences are underscore ID, so every document you have, once it's persisted to the database, has to have an underscore ID, which is basically the primary key for the document. It can be anything you like. Has to be unique, obviously, but if you don't create one, we will use an object ID, which is based on like machine, timestamp machine, and process and things like that. And also here we have an example of the date. So, JSON's great, but it doesn't have, or doesn't deal with certain data types very well. It's kind of a limited subset. So we extended JSON out with a spec called bson, which is a sort of superset. It allows you to deal with things like dates, 32-bit integers, 64-bit integers, IDs, binary data. And it's how we store everything on disk as well. So it's kind of optimised for us to be able to scan through it and read through that data. And all the drivers themselves send it across the wire using bson as well. Right, finding data. So as I said, one of the goals was for it to be rich, so you can do ad hoc queries very similar to the SQL world, and finding data is the same sort of thing. So here we have, you can do regular expression searches, you can check if tags exist or fields exist. Because your schemas are flexible, you need special operations to do that. There are various operators you can use, so you have ranges for less than equals, greater than. But the way you do your queries is you actually provide a document, sort of an example of what you want to match. So it's very declarative. So up here we have author as the key, and we're passing in a regular expression to find any authors that begin with R. And you can build these queries by passing through the document that is an example of kind of what you want to find. Yeah.
How expensive are queries with regular expression?
So regular expressions, how expensive? This one is expensive because this one uses a sort of a case insensitive, but it will still use the index. If you anchor a regular expression that's not case insensitive, it can use the index for the lookup. So it's not expensive. If you do one that is just anywhere in midstream, you have to scan through all your documents that match the other parts of your query criteria. Indexing, well, there's lots. I mean, you can do compound indexing, same as in the SQL world. You can return data straight from the index if you do your queries and just return data that you store in the index. You can index arrays and you can index full objects as well. So there's kind of many levels. You can index sub-objects and sub-arrays and things as well. So here we just have an example where we're indexing author, and then we're doing a find and using that index. Underscore IDs, as I say, they're the primary key, so they have an index by default anyway. So if you have a complex underscore ID, you have an object, for example, you have that index that you can use for lookups as well. You can have up to 64 indexes in a collection. Don't have that many, because when you write to disk, you have to write in 64 places, or 65 places, including the document. But these are very similar to the SQL world, and kind of you can tune and examine your queries in a similar way as well. So if you're just using the shell, put the explain command afterwards, you'll get back information about how your queries run and some statistics. So here we're using B-tree cursor, so that's telling us we're using an index, and then author is the index name that we're using. Things like n-scanned and n-scanned objects are to deal with how many things we're looking up in the index compared to how many documents we're looking at. We only have one at the moment in there. And then we have index bounds as well. So when you're writing your application, you can turn on what's called the profiler. You can just do it in the shell, turn it on, and you can examine your queries that take over a certain period of time, or you can examine all your queries if you want to. And just like in a SQL application, you want to understand what's going on under the hood and find out and ensure you're using indexes to return your data efficiently. So, atomic operations. When you want to update your documents, updates themselves are atomic, so the document is guaranteed to have that update put to it. But we don't do multiple document transactions, so if you have to do that, people write that out in their code. It's kind of convoluted, but it can be done. But here's an example. What we have is we have set and unset and increment operations, and then we have some array operations as well, so push and pull from arrays. So here we're creating a comment, and all we're doing is we're just adding in a new document. But the interesting part here is when we actually go and update. So the first thing we're doing is providing a query for what we want to update and match. So here we just have an example of an ID. And the second part is kind of what the update is. So we're doing a push, and we're pushing to comments, the new comment, and we're doing an increment of comments count. Now, the interesting thing about this, or the good thing is when you come from a developer's perspective, is you don't have to check if these things exist in your code already. If you're using a push, that means you're dealing with an array, and if you're using an increment, that means it's a number. So we're pushing to comments. We don't have to check if comments exist and set that. We can just push it on, and when we go and query again, it will just add those on into your document. And this means your code as a developer can be kept relatively short and concise and do exactly as you need. Some other aspects that are interesting, should you need it, we have geospatial support using there's two models now, but it's all 2D. You can either have a flat world model or a simplified spherical world model. And all you have to do is just ensure a 2D index. And then you can use things and you can find things within bounding boxes, or find points within a distance, or points in the polygon, those kind of searches. It is all point-based, because we only have B-tree indexes at the moment, so there's no polygon queries and things like that at the moment. One other side of functionality that's built in on all the drivers is something called grid FX. Now this is using the database as a file system and then saving files into the database. Now this example here is in Python, and apart from FS, everything else is natively dealing with exactly how you would normally deal with putting files into the file system, or how you would read them out. So this is really simple, it's very useful. Behind the scenes it does some special things. It stores the data about the file in one collection, and you can add metadata essentially to it. And then it stores the actual binary of the file in chunks. They're split up into chunks and stored in another collection. But when you stream it out via a read, it'll actually just go through and get all those chunks and stream them out to you. The reason why it chunks it up in the first place is because any document in MongoDB has a limit in size. There's a maximum limit of 60 megabytes, so which was the same for our commands as well. So, but by default, it splits them up into, I can't quite remember the size, something like 40k or something chunks, and then you can skip through and go through at different points of the file as well, should you need to. Obviously, it's not going to be the most performant network file system, but if you want to simplify your stack or have a small use case, people will put that behind things like Varnish, or have the Nginx service directly out of MongoDB as well. One other thing coming up in 2.2, or in the next release, which is due next month, is the aggregation framework. So currently, if you want to do any detailed levels of aggregation in MongoDB, you have to do a MapReduce. And the way we do MapReduce the way we do MapReduces in MongoDB is you supply a JavaScript function. It takes the JavaScript function, translate the documents out from your query, from C++ into SpiderMonkey, runs them there, and then pushes them back into the C++ runtime, and then pushes them out to the user. The translating between the environments is slow and costly, and SpiderMonkey is single-threaded as well for us. So people have asked for something better, and we've now produced the aggregation framework, which, just using the aggregate command, allows you to provide a sort of pipeline, an array of operations you want to do on your data. I could show an example of this later on, but basically it allows you to rescope your documents on the fly, do counting as well. You can move things up and down in the document as well, depending, so you can totally reshape and reproject your documents should you need to. So that's coming up in 2.2, and it's available for testing now in the 90s. So, talking about data modeling in general, or to reiterate, it is schemaless. You can choose your design of your documents depending on your need. You have very flexible data models, but not all models will scale very well, and you have to, when you look at schema design in MongoDB, you have to understand it's all about your data usage. So if you have a complicated document which has an array in it and subdocuments inside, and you need to do aggregates across all the subdocument elements, then having them inside a document isn't necessarily the best way to store your data. Because when you do queries in MongoDB, it's all about finding documents and not finding portions or sub-elements of subdocuments. This is a common mistake that people will do, and they may have to refactor their sort of design to be able to make that scale out across many, many shards. But yes, so that kind of covers the document side. I'll just very quickly just talk about where you can use it in case you don't know. Basically, we support every language. 10gen supports every popular language. Node.js has recently come in with us as well. And the community, via evangelists as well, supports some of the more or less popular languages or upcoming languages as well, depending on your perspective. But basically, you can use it in any language you want to, and you can access it, and there should be native drivers there for you. I'm not going to go too much about how people already use code, so I'm going to skip past these. Has anyone got any questions about querying it and that side? Sure.
It's about data models, and you said that you've got very agile data models, Now assume you get onto a project very late and the data models have been made. How would you find out about those data models? Do you actually have to look at the code to find out what's in the database?
Yeah, so that's a great question. So yes, we have, because they are so schemaless, it is up to the application to enforce what's in those data models. Now, some people do stuff extremely rigidly, will ensure that things meet a schema, and I myself run a Python library that allows you to define schemas in your code, does like form validation and things like that. But essentially, to validate every single document, you have to go through and look at it, because you can have different style documents as well. Now, that may be a negative, but generally people don't go in there into your database and put totally different documents into a collection, for example. And it allows you potentially to iterate over as you change your data models in time, allows you to, in your code, just accept current levels of, or current versions of a document and update them should they be needed. So it depends on your problem or your scope as well. But yes, there's definitely a chance that your documents can look totally different, have different keys and values throughout. And there's no real way, unless you go through every single document, to find out what the full schema is that you have in that collection.
Will there be a standard way to define the schema?
No, I don't think there will. There may be in the future. We're looking at things, because it is expensive to store schema at the moment, because we store the field name alongside the value every single time, so that can be a lot of duplication. It can take up some disk space, but certain developers will worry about that, take up large amounts of memory potentially. So in the future we may store some of that data as the most common parts of the schema in a sub-collection in MongoDB and allow it to be stored in a more compressed format. But that's kind of not finalised yet by any means.
Yeah, what kind of spheres may I use if I work with geographical data?
So they are, they're either flat world or like a really simplified round world version. So there's just two different types of, you're going to hand them out? Cool. There are two different types you can do. So you can just do near models, which is the flat world. And an example of using that is, I don't know, if anyone's played like Words, which is like a Scrabble game on Facebook, that uses the flat world model to work out where the tiles are. And then for the round world model, for geographical, to try and get distances, Foursquare uses that, and it's just very, very simplified. But you can't reproject different types of projections. I think it's just like the globally. So
it's the GPS model.
Yeah, it's the most simple model. So yeah, it's not. I wouldn't use it for working out distances between areas at all, in terms of if you needed any level of millimetre or even metre correctness. Okay, so I can now talk about high availability, and kind of this will be how replication works. There's two sides to scaling with MongoDB. The first side is all about replication, which is basically you duplicate your data so you can handle things like data centers going down, losing machines, rolling upgrades, trying to get a higher percentage of uptime. Or you can do things like have a machine that's used for, or have a cluster of machines that's used for your core operations, and have certain machines with copied or replica data for your analytics or backups, something like that. So, how it works is it's actually extremely simple, but a replica set has to be made of 2 or more nodes. And when you set it up, you just put in a command line flag and say you're using a replica set, and you add the configuration, add the nodes to it, just simply through the command line. And what happens is an election is called. Now, as long as there's over 50% up and visible, then we can create a primary. So if you have 2 nodes and you lose one node, then it's not over 50%, you'd go into read-only mode. But here we have 3 nodes, and then an election will create a primary based on who's got the most up-to-date data, and there's some other things you can do with prioritization. But up-to-date data is the key for all of it anyway. And what the secondaries do is they'll read from the primary's op log, which stores all operations, and they'll apply them to their own data sets. So they're reading, and the data is essentially duplicated out to your secondaries. MongoDB is a single master system, so the primary is the only place you can ever write to. By default, it's the only place you read from, but you can set up your read preferences to allow you to read from the secondaries. And then, if the primary fails, you take it down, you have to do some operations on it for whatever reason. The other secondaries, the remaining members in the set, will call an election, and between them negotiate who should become primary. As long as 50% is visible to them, a primary will be elected based on who's the most up to date. So, during that time of the election, your application is read-only. You only have secondaries available to you, so you can't accept writes. So your application will have to handle that and be able to deal with it. Some people put loops and tries, other people will throw an error back to the user. It depends on your system and what steps you'll do. So when the election happens, we'll have a primary again. It will replicate its data out to the secondary. Say our third node comes back up and is recovering, and what will happen here is it will check the new primary's op log, and then it will start reading those operations and come back into the set. Now, there is a window of opportunity for the primary, the original primary here, to have had more data that hadn't been replicated out to your secondary. So during the recovery phase, if this happens, it will dump it out into a directory with your data files called rollback, and you have to manually work out how you're going to deal with that data, either merge it back or make a manual decision, because it can't automatically say whether that data should or should not exist. And then, the replica set is now re-established and you have your new primary. So that, in a nutshell, is how it kind of works. It does create some interesting scenarios or features that you can add on to that. So one part is write concerns. By default, whenever you do an update or an insert on MongoDB, it will just fire and forget that insert. So what that means is it won't even check to see if the database got the command at all. This is the one default which I would argue is not sensible, and most people don't want that. It may be fine if you're just storing logs or something like that, but for most operations you don't want that. So you can call and set the write concern and say, I want to make sure it gets applied to memory, or I want to make sure it's written to the journal, or I want to make sure it's flushed to the disk. There's sort of varying levels, more control over actually where your data gets put in MongoDB than most databases. And when you start having replication, you can ensure that it hits a number of your replicas. So you can say, I want to make sure it hits the majority of my replica set before you go on to the next operation. So basically a block until one of the secondaries has returned that back. You can also set up your nodes and tag them and give more information and say, I want to make sure it goes to 2 of my data centers, depending on how you tag and set up your data. Other things to know, you can use it for scaling reads, but it's not guaranteed to be up to date at all. And your application has to be able to handle your reading from a secondary that could be an hour out of date, depending on how your operations and how the system is loaded. And as I say, you can prioritize. So to give an example of a setup that we've seen in the UK, is we have people that have their primary data centre in London, they have a secondary data centre in Reading, and they have something in Amazon, just to make sure it has a copy of the data. London is where they exist and is where most of their users are, because it's an internal application, and they ensure that that has the highest priority. So the idea is always one of these two will be a primary as long as London is up and running as a data centre. Reading has one that will be has more likely to be a primary than the cloud database, and has a backups and analytics server that will never become a primary because that's a priority of 0. We have, recently in America, AWS went down. People who split their replica sets across their AWS clusters or availability zones were able to handle that. They lost one and they couldn't write to it, but they were still able to serve and stay up because they had their data spread across and their shards actually spread across these availability zones. So it allows you to minimize risk depending on your risk concerns. So there is a lot of configuration and more nuts and bolts in replication and more options for how you use it than any other part in MongoDB.